All right, I'm John Buther. I'm going to explain the algorithms that we're using. The first one is support vector machines. An SVM is a sort of classifier. It answers basically a yes or no question about a piece of data. You can sort of see down here where it was classifying the blue versus red. It just separates it out. It can work on any sort of data. Basically, if you have a whole bunch of information and you don't know how this information is connected at all, you can basically throw it into a support vector machine and it'll give you an answer. And so the way it does this is it uses machine learning and it builds these kernels. And basically each kernel takes all of the data, it comes up with a number, and it adds it to your solution. And then if your solution is above a threshold, the answer is yes, and if it's below, the answer is no. And the kernels are pretty arbitrary. It's well suited to an FPGA because each of the kernels can be separated. It's very parallelizable. Our SVM data is going to be about 1,000 dimensional, and I guess that's really all there is to say about that. Until I get up the histogram of origin gradients. This is what provides data to our support vector machine. We take the image input, we compute gradients, and if you don't know what gradient is, anybody know what a gradient is?
No, I was just going to ask a question. What is a kernel mathematically? Is it a function?
A kernel is, yeah, basically a function.
Okay.
And so you're computing the gradients, and then for each pixel, and then you're taking those pixels and you're putting it into, you're basically collecting them into a cell, and then you normalize this cell over space, and then you take all of these data and you throw them into the support vector machine because you don't really know what any of them mean. It's demonstrated to be able to do high-speed pedestrian detection. There's a lot of papers written on this, and it's actually well suited to detect many sorts of objects like bikes, cars, trees, trash cans. And down here, this is from one of the papers that had this working. So it's very similar to what the team last semester did, or at least part of it is. Gradient detection is very similar to edge detection. It just uses a different, basically, matrix for multiplying the picture by. And the gradients are then, of course, binned into cells, and the cells are concatenated to form data vectors for the support vector machine. And basically what you end up is something like this, and you throw it into the support vector machine.
All right, so I want to talk about a little of the things that we're going to be delivering. We wanted to deliver a real-time system. The group from last semester was only processing like a few frames every minute or a frame every few seconds with whatever their hardware spec was. We wanted to do a system that would be able to process an image and compute it in less than a second and display anything that we calculated with an overlaying map. We're taking advantage of actually more parallelizing the hardware. We're going to try to process many different blocks of the image all simultaneously. So we obviously wanted to deliver it on this hardware. And one of the other design goals was to actually create a P-core, which is a specialized just hardware block for Xilinx projects. Xilinx would like to be able to deliver our object detection to other companies. They work with tier 2 automotive suppliers. Xilinx is essentially a tier 3. And they would like to be able to say that we have this system or this block that you can use, put it on our board, and you can implement higher level algorithms to go with it. That way they can, we would like to detect a moving object. So we would be detecting the objects, and maybe they would like to compute moving in a different direction or create new vectors from that so that they can do whatever they wish to do with it. So we're doing like a baseline core for them. Any more questions? Sorry, are there any questions?
Any questions for the class? Okay, I have one question, which is a hard question for me to ask because it might expose my stupidity. Everybody may know this. What's a Z camera?
Oh, a Z camera is a specialized depth camera. They're very expensive, which is why we're not using one, but it would essentially give us a third dimension to use. So if you have 3 dimensions rather than just the
3D
planar,
camera.
it's
Yeah,
sometimes easier.
it's like the Microsoft Connect. They brought the cost down hugely, but there's a whole bunch of other stuff we would have to play with to get that to work anyway.
Okay, so you're basically going to use the same camera setup they used last
Yes.
time?
Yeah.
Okay. Was I the only one who didn't know what a Z camera was? Oh, okay. All right, thank you, and thanks for jumping in first.